Let's go ahead and get started and talk about the agenda today. So I'm pleased to be joined by Dan as well. I'll do a little overview of convergent science for those of you who don't know who we are. And then I'll talk about certainly our after-treatment features and some of the validation work that we've done on those features. I'll talk about some of the urea deposit modeling approaches that are used in the industry today. It is a rapidly changing area, but it's certainly trying to address a key need. I'll touch on, you may have seen a webinar that we did a little while back with Isuzu Americas, with Yang Sun of Isuzu Americas, and we did a paper with them as well. They're an early adopter of our urea deposit prediction capability. So I'll touch on that study. And then Dan will take it over and talk about some of the things that we're doing. He'll describe your detailed decomposition for deposits, and then what we've done to accelerate those deposit simulations and give you a demonstration, a live demonstration of how you can use CONVERGE with its autonomous meshing to rapidly make design changes and implement them to meet a rapid prototype design situation. Let me go ahead and describe convergent science for you. We started in 1997. You can see a picture of our pretty headquarters up there in Madison, where Dan is right now. I'm down in the Texas office. We have offices as well in Detroit and in Europe and in India, in Pune, India. Since 1997, CONVERGE did a lot of consulting work and ended up developing the code that became CONVERGE. In 2008, we were able to sell that commercially. Since then, we've been extremely successful at selling that in cylinder combustion, and I'll have a slide on that next. I joined CONVERGE about 5 years ago to help them go into gas turbines, and then rapidly also took on helping go into after-treatment in 2014. So it's not the first time we've been doing after-treatment, but we certainly have learned a lot and have, we feel, become very competitive. And then we also do pumps and compressors and things like that. So there's a lot of other things that CONVERGE does if you're more familiar with us from in-cylinder combustion. We have a lot of partners that we work with routinely, and we look forward to partnering with you if you don't see your logo down here. So CONVERGE primarily originally started off as good for reacting flow inside of the cylinder for combustion, but we've also moved into doing after-treatment simulations as well. So as you can see down here, the adoption cycle of CONVERGE for in-cylinder simulation is pretty significant. So there's a substantial, very good chance that whatever car or truck you're driving, the manufacturer uses CONVERGE to design what happens inside the cylinder. And all of that leads to trying to help in other areas or seeing areas where CONVERGE can be applied. We're here to talk to you today about after-treatment systems, like you see a urea SCR simulation here on the right. We also do gas turbine combustors, and I did mention pumps and compressors. And there's a lot of areas where if you can think of a complex geometry that might be moving, maybe not, but a complex geometry with chemical reactions and where automatic or autonomous meshing will help, those are certainly areas where CONVERGE is applicable. Let me talk now specifically about urea deposits and some of the design challenges that after-treatment system or ATS system designers face. Of course, they're all trying to meet emissions regulations in a cost-effective manner. Every time I talk to them, they're telling me they have less budget and less people and time to get done the things that they used to do in the past, their design projects. So they're looking for fast and accurate or fast and effective design processes that can help them meet their timelines. The other key driver is the move towards more compact urea SCR or after-treatment system designs. Gone are the days of the long inline systems, and now we're looking for systems that fit underneath the hood, and they're also low temperature to try to improve efficiency. And that poses some specific challenges when we look at urea deposit formation. certainly you're going to rely on effective splashing and filming of the Urea-Water solution. And those films can be in the temperature range that we know forms deposits, like you can see here around this injector. So urea deposits are consistently the number one thing that manufacturers tell us when we talk to them about what their challenges are. They don't have a solution for this. They have ways of assessing it, and I'll talk about in just a second, but they're really very much seeking a solution in this area. Just a quick overview of CONVERGE for those of you who may not know about us. We are an autonomous meshing code, so you'll never make a mesh again. Once you set up a CONVERGE model simulation, if you want, very simple to change the controls where you choose the base mesh size that you want to use. You choose whatever embedding that you might want to use around a wall or near a spray. And then you select Adaptive Mesh Refinement, AMR, which is a key way to add mesh automatically when and where it's needed in areas of high gradients of, let's say, velocity, for example, with after-treatment systems. So once you've set up your case, you can change that mesh literally as fast as you can change your shoes. So one of the key factors with CONVERGE or value propositions is complex geometries and not ever having to make a mesh again. That all comes with advanced spray models. You can go anywhere from modeling just shooting droplets of size and size distribution with secondary breakup to actually modeling primary and secondary breakup. We have a lot of studies on that. When we talk to urea decomposition, we have two general approaches, and I'll describe them as simple decomposition. That's either using molten solid or multiple component approaches, where urea goes in one step it decomposes to hydrocyanic acid and ammonia, and then the hydrocyanic acid in another step decomposes to ammonia. So really it's just a single step for the initial urea decomposition. That's the dominant approach that people use in the industry today in CFD. The problem is you don't get any information about some of those reactions that occur that create these crystalline solids inside of the film that are very difficult to get rid of. And that's why we also have the detailed decomposition approach that we've developed and implemented in partnership with our friends in France from IFPEN. So we have those two dominant approaches, and we'll talk about those today. We certainly have liquid wall interaction models, the familiar Kuhnke and By-Gossman models that you probably are familiar with from tools that you use today. We have each of those. And those also include the Ruck drywall cooling models and the Leidenfrost effect of let's say a droplet on a hot skillet type effect models as well. In order to accurately predict films and deposits, you have to get the wall temperature right. So we have good, fast conjugate heat transfer with supercycling. And in order to model urea deposits, there really are two primary approaches, and I'll describe those in detail. One is to do a urea deposit risk analysis using simple decomposition. That's the more common way of doing it. But what we also have today is the detailed decomposition, where you can actually model the deposit formation. We're not talking about SCR surface chemistry or NOx reduction in the catalyst today, but we certainly have that capability with most of the other after-treatment catalytic devices as well, either using CONVERGE's internal surface chemistry capability or linking it to your surface chemistry tool of choice, whether it's GT Suite or Axi Suite, or perhaps something you've grown on your own. Talk very quickly about spray wall interaction models, because this is a key capability that you have and you have to validate it. When the droplet hits a wall, there's different regimes that it can go through, whether it's rebound, thermal breakup, deposition, or splashing. And the Kuhnke model that I'm showing here shows an effect of the wall temperature on that droplet and how it affects the actual formation of a film. And those that do this kind of work know that there is a T-star or critical temperature at which this transition occurs. And of course, we have that capability as well. And then we do also, in some situations, you may find that an adaptive film mesh will help reduce grid dependency, and so we do have that capability as well. So let's talk about validation cases. The nice thing about after-treatment systems is that they have some very well-accepted published validation cases. We're talking about single droplets here, where we're able to predict using, comparing against the data of Wong et al., able to predict the initial reduction of the droplet size from water evaporating, which is faster than the urea decomposing, and matching those data at various temperatures. And then when you look at urea sprays, not hitting a wall yet, but just sprays and its conversion efficiency from urea to ammonia at different temperatures, we're able to predict the data of Kim, which is another very classic experiment. So we're able to predict those very well. On spray wall interactions, there's the famous Birkhold spray wall model, and we're using that as one of the key validation models in the work that we'll present today. And that's you have hot air flowing on the top and the bottom of a plate, a 2 millimeter thick plate that then has pulsed urea water spray on it. And you have to identify what the temperatures are in the plate as it cools before the film forms and then as the film forms. So that's a key validation experiment. This experiment down here talks actually about the getting into the SCR, where we've taken some data from our friends at Southwest Research. Zainal Abidin did a study, and we were able to match the emissions reduction using GT Suite in that case, but also we've done the same thing with our own internal surface chemistry. So this slide is intended to show you that we've done our homework on all of the key validation cases for urea SCR performance. We have obtained good results on those, so we feel comfortable about our process. So let's talk about ways that different people look at assessing urea deposits. Show a picture here of a mixer wall temperature. It does have a film on it, even though it's not being shown. But if you look at the different approaches people use in after-treatment system modeling, 0D, 1D models like GT Suite and Axi Suite and the like, they just don't incorporate the 3D spray and flow, so they're sort of not effective in that area. And really, effective CFD certainly has the ability to aid design and troubleshooting. Hopefully you do fewer tests, but maybe what ends up happening is the first test you do is a better quality design, and at the end of the process you have a much better quality design, or you can troubleshoot issues in the field. The key thing that we all know for CFD to be valuable is it has to be predictive, and it has to be fast enough to meet the design pace. You can come back with your simulation result in 3 weeks, and the design team has already moved on. So crystalline deposits, we know that they form in a narrow temperature range. So if you use simple decomposition and you identify which of these films are in the right temperature range to form deposits, and then you look at some other key transport and some other factors that might affect deposit formation, you can develop a semi-empirical relationship to predict that deposit risk. The problem that you have is while you've identified where it's risky, you don't know if it actually happened or not. So you really have no information on crystalline species in it to either inform your design or to look at regeneration strategies. So what we'll talk about here today is directly modeling those crystalline deposits, and those are B array that also form CY and amylate that Dan will talk about. So the question you should think to yourself is it predictive and is it fast enough? Here's some results from our deposit modeling in our current version, where it's identifying of the films that are on the surface, which of those films have certain risks. And I'll talk about in the next slide here, this actually being applied to a commercial design case. This is a study that we did with an early adopter of our urea deposit capability. Young Sun took the lead on writing this paper for Isuzu Americas, and so we were happy to have not only them as an early adopter, alpha tester, but also to share the data that they had and its performance with CONVERGE. So it's a medium duty diesel truck, and it's an after-treatment system study that was aimed at sort of maximizing the overall NOx reduction you can get out of this system. So the urea is injected here. There's a decomposition tube that we're looking at here. And we know that if you put too much urea in at certain conditions, or DEF, that you'll begin to form deposits. And so their goal was to try to increase that DEF dosing limit so they could maximize the NOx reduction. So if you look at this paper that was presented in April of this year's SAE that Yang presented, you can see that there are deposits that do form here, these little white deposits here. And sure enough, when we ran CONVERGE and looked at the film temperatures and did a risk analysis of them, the CFD prediction shows exactly where the highest risk occurs, and that matches or correlates well with the actual deposit formation. Now, that, like I said, that's great information to have, but it doesn't tell you what's in those deposits. And so that was one great benefit we had was Isuzu Japan did the experiment, and they did analysis of those deposits. And you can see their chemical analysis of those deposits up here. And the key thing to point out is the ratio of amylide to cyanuric acid. These are two of the crystalline species that decompose at very high temperatures and are hard to get rid of. And you can see from our simulation here that we were getting about the right ratio, even though we were running a very short amount of time, about the right ratio of those deposits. So that made us feel that we had the right ability to predict where the films occur, and actually the chemistry in the mechanism were working well as well. So now what I'll do is or what this leads us to is that the approach is working. We just really need to speed this up, and that really gets to a lot of the good work that Dan's done this year. So I'll pass the ball over to Dan now.
And as Scott has shown some of the results with our detailed decomposition model, the work with the Isuzu has shown the accuracy of that model, not just for academic lab studies, but on a real after-treatment system with pipe ends and cooling to the outside, convection, and complex geometries. So now that we have that validation, both fundamental and applied validations of the detailed decomposition model, the next thing we really need to do is to speed up our simulations so that we can bring those kind of accurate predictions to timescales that are more informative for system designers. So as well known in the industry, the solid deposit problem is really the main problem that's facing the industry now in the application of the Urea-Water solution-based selective catalytic reduction. So some problems that come along with that are reduced NOx reduction, because deposits such as we see from Isuzu's system tie up a lot of ammonia that is intended to pass through the SCRs tied up in those deposits. We can have injector blockage. Once the injector is blocked with the deposit, then that interferes with the spray. So whereas a DEF injector is designed to produce a given spray with a known size distribution, solder mean diameter, and velocity, when a deposit gets in the way, then it totally messes up that spray, and that injector is not behaving as expected. And lastly, those deposits, in addition to tying up ammonia, they also form significant pressure drop. So what is often done is a regeneration strategy is done where additional diesel fuel is burned simply to raise the exhaust gas temperature to remove these deposits. And in a push towards higher fuel economy, using more fuel to get rid of deposits is certainly counterproductive. So when it comes to simulation, the challenge really is widely varying timescales. So spray transport from when the spray is first injected to when it first interacts with a pipe wall or a mixer is on the order of a few milliseconds. So the that spray wall interaction leads to a rebounding or a splashing or a film formation. So then we move on from milliseconds to the amount of time it takes for a film once formed to move. And it takes on the order of at least minutes for that film, once initially formed, to move down the pipe wall. It's subject to shear, and it's subject to gravity, and it's subject to those forces, so that the deposits, as shown here and in academic work, often the deposits do not form at the initial impingement location. So it's not enough to run our simulation for even just 1 or 2 seconds. We need to see where that film is going to move to after, let's say, at least 1 minute, maybe 1 or 5 minutes. The wall temperature is also a key aspect to accurate modeling of spray wall interaction. So there's a very interesting two-way interaction that occurs. As Scott showed before, the spray wall interaction models, the Kuhnke or the By-Gossman, indicate that the wall temperature is key to determining the spray wall impingement outcome. The interesting two-way coupling is that once we start spraying on walls, they cool down, and we may go from a non-filming condition to a filming condition. So that's why it's important that we resolve the wall cooling accurately, and that usually takes on the order of 1 to 5 minutes for system walls to reach their equilibrium temperatures. And finally, the deposit formation or the deposit chemistry typically takes hours. So we know that film takes minutes to reach its equilibrium positions on the surfaces, and for the actual growth, via addition of new urea through urea-water solution dosing, and through that chemistry to take place, we need hours. So we're moving towards these longer time scales with an approach that allows us to capture the key physics accurately, which in this case, the key physics is what's happening with the spray and the film and the wall temperature. And we find out that we can make some approximations with the gas field that allow us to have greatly accelerated runtimes. So now we'll step back into the chemistry a little bit here. So we'll talk about this detailed decomposition mechanism that Scott alluded to. So as we know, the purpose of injecting urea-water solution is to produce ammonia. So in the desired pathway, 1 mole of urea, once the water evaporates, will yield 2 moles of ammonia. However, what was identified quite early on, Nishioka et al. In 2006, is that we see the formation of biuret. So biuret is formed when isocyanic acid from urea decomposition combines with some of the non-decomposed urea. So we note on the right that biuret is starting to get to a heavier molecular weight. So we see it has 2 carbons as opposed to 1 for urea. So similarly, once biuret forms, then more and more ammonia combines with biuret to form, consequently, cyanuric acid, amylide, amylene, and some melamine. And these compounds are very problematic because they form at a certain temperature range, and then they take a much higher temperature in order to be decomposed. So it's really the high temperature stability of these compounds, of these ring compounds, that make the deposit problem what it is. Now we can look at some of the formation and decomposition rates of these specific chemical compounds. So there was some excellent laboratory work done by Shaber et al. And this work was kind of replotted here by some more recent authors. And what we see here is we have different colored curves for different components. And what we see here, first of all, happening around 175 Celsius is that we see urea is decomposing. So what that means is we heat up a sample of pure urea was heated up, and we see it starts decomposing at a high rate of 175 to 200 Celsius. But then if we look below the axis, we see that the first compound being produced is biuret. So we see that red curve. So biuret is first produced from urea decomposition, but then it kind of follows urea at a slightly higher temperature, and we see that the biuret is decomposing. So the very next key step is that once biuret starts decomposing, then we see formation of cyanuric acid, amylide, melamine. So we can see that these very high molecular weight compounds are being produced between anywhere from 200 to 250 Celsius. So the real difficulty lies in that they are not decomposed until higher temperatures of above 275 Celsius. So we have this cascade from urea to larger and larger molecular weight compounds. The better understanding of that mechanism will allow us to avoid the production of these in real systems. So that's why we worked with IFPEN, and they developed a 12-step chemical kinetic mechanism. We can see schematically on the left that we have the desired pathway through reactions 10 and 11, but we also include the non-desired chemistry, the deposit chemistry. So this 12-step reaction mechanism includes both the simple desired deposit decomposition and also the complex deposit chemistry. And that has been validated with work of Lundstrom for gas release and with thermogravimetric analysis of Schaber et al. 2004. So now, after reviewing the chemistry, we'll jump back into a technique that we call frozen flow. And it's this technique that's giving us a very good speed up compared to our traditional approaches. So one thing we notice right away is if we compare the momentum flux, which is added to the domain from an injection. So momentum flux there, we know the liquid density, the nozzle area, and the spray velocity, which is squared. So if we compare a diesel injection using typical numbers, we get 16 kg meter per second squared. But then if we look at a typical urea-water spray injection, which has a much lower nozzle size and a much lower velocity, we see a 0.003 kg meter per second squared. So what we see is that this momentum, which is interacting with the gas phase and will cause eddies and will cause recirculation in the gas phase, is less than 0.02% in the diesel case. So we see a huge disparity, and we think, well, maybe we can take advantage of that. So we find that we can. So the major thing we take advantage of is that with steady inlet conditions, which we typically have for exhaust flows, we have a known mass flow rate at a known temperature. The only forcing function on that flow to cause the flow to change is the spray. So when the spray turns on or turns off, we might see a small change in the flow field, but otherwise the flow field does not change much. So what our approach is to track the spray injections, the film, and the metal temperatures at all times. We capture them in a time accurate way, and we're able to use large time steps between spray pulses. But we only update the flow field when we really need to. So what that allows us to do is to reach large physical times in the range of minutes in reasonable compute times without scaling of physical properties, which has been done previously. So here we see some runtime comparisons. With our older methods, we would be able to achieve about 10 seconds with the molten solid approach, which is the simple decomposition that Scott mentioned before, where urea simply goes to isocyanic acid and ammonia. And now we're able to get about 60 seconds of simulation time per day. With detailed decomposition, due to improvements in how the code is written and how that code is made more compatible with native converged data structures. We're also able to get 60 seconds per day. So in some actual customer cases, we're able to achieve these high simulation runtimes, which means that overnight you'll see what the film has done in 1 minute. And similarly, if you wait 5 days, you can see 5 minutes of progress. So these times are much more correspond to the timescales of film movement and the early stages of deposit formation that we simply could not capture before. So of course, when we have a new approach, we need to validate it to ensure that that this approach really does capture the key physics. So the experiment of Burkhold et al., very fine experimental work was done where a plate in a rectangular channel with gas flow had basically Urea-Water spray onto it. So Burkhold, you can see his experimental results on the left with X's. He varied the initial temperature and the ammonia and Urea-Water dosing rate. So you can see at a higher temperature, there's a slight amount of temperature decrease when the duty cycle is increased. When it's doubled, we see that we have a lower final temperature. And finally, he looks at another condition with an initial temperature about 340 Celsius and a 20% duty cycle dosing. So the key thing to note in all these conditions is that we never see any film formation here. So there's wall cooling due to the spray wall interaction and that Leidenfrost effect, which we capture through the RUC model, which is an analytical model to capture that drywall cooling effect. So our simulation approach, you can see our results on the right in the solid curves. Now, at a first glance, you would say we have quite similar results to what we have on the left. That's the solid lines on the left are Burkhold's own simulation. But the approach is quite fundamentally different. So Burkhold et al. Reduced the metal specific heat or the metal thermal mass of the plate by 150 times. So what they did was to reduce the specific heat of the solid and therefore stretch out the time axis. So the simulation is really 1 1/3 seconds. They multiply by 150 to get 200 seconds of physical time. Our approach, on the other hand, solves 200 seconds of real physical time. So the approach is quite different. And one interesting detail is if we focus in on the inset on the right, if we look at the cooling curve for condition A, which is the highest temperature condition, you can see that our simulation shows a rapid cooling from an injection pulse and then the partial reheating recovery towards the condition without spray. And then we can see these repeated cycles of cooling and partial reheating, which is not even resolved in the experiment, in this experimental data set. So that's the kind of detail that we're capturing in the metal temperature history, but we're still getting these quite good run times. So another very important effect of that is that for these simulations, for experiments, Burkhold used 2 Hertz injection. So in every 1 second, there's 2 injection pulses. So that means in this on the simulations on the right, we stayed true to that 2 Hertz injection for 200 seconds. That gives 400 pulses. So on the left, work by Burkhold, they were looking for a first approach in order to get the time scales of cooling that they saw experimentally. So there's no fault in trying to find a way to represent that physical time, but we feel we found an approach on the right which injects the correct amount of liquid mass. So instead of injecting the correct liquid mass divided by 150, we have the actual correct injected liquid mass in our simulations. So not shown here is that the liquid mass actually, for the filming case, which that brings us to, those prior cases do not form a film. For the condition in which a film does form, we see that the liquid film increases until it reaches a steady state, which means we have run through enough physical time in order for a balance between new liquid addition and evaporation and decomposition to have been reached. One important thing to note also is that from the last slide, the coolest condition did not form a film due to the low dosing rate. Experimentally, Berkhold simply doubled that injection rate and formed filming. So that's what we did in simulation as well in Converge. So we doubled that injection rate. We didn't tune any numerical parameters additionally, and then we saw that we were able to see the film formation here. So the video on the right shows just a close-up in time on one of the injection pulses. So this is near the end of the simulation, around 100 seconds, where we have nearly reached a steady temperature distribution in the plate. So if we look at the plate, we see that we resolve that cool area very nicely, and it's smooth because we have the real specific heat, real properties. So this is the spray we see here is simply one of hundreds of injection pulses. So finally, we want to highlight another key advantage of Converge, which is our ability to do rapid prototyping or quickly change out a geometry.
This is a typical diesel exhaust aftertreatment system. We will demonstrate how to replace the splash mixer with a completely new design and prepare the surface for a new simulation with Converge. The first step is to delete the triangles associated with the boundaries we wish to replace. We select the mixer pipe, the mixer, and the mixer ends. Note that we delete the triangles but not the boundary definition. Next, we replace the mixer pipe. We go to Create Triangle, and we loft edges between the two sets of open edges, which are highlighted in yellow. Now we click Apply after assigning the boundaries of the new triangles to mixer pipe. Now mixer pipe has been recreated, and we're ready to import our mixer. We go to Import. We import the STL file created from your CAD package. We import it into our case setup, and we've placed it so it's in the correct location in this new in our geometry. So now notice that the mixer extends beyond the pipe walls. We've seen the green tips extend outside of the domain. We hide all the boundaries and just show the non-assigned triangles in dark green, and we see the shape of the new mixer which we want to use. We go to Repair Polygonica to use a third-party Polygonica tool available with Converge Studio. We first select the boundaries of our existing geometry, and then we select the not assigned boundaries of the new mixer, since they will be subtracted from the existing model. Polygonica has finished the Boolean operation, and now we can see that the mixer no longer protrudes from the pipe. Again, we hide selected boundaries so that we can see the mixer is still inside the pipe, and any surfaces which do not intersect the outer wall are unchanged. Next, we assign the triangles by boundary. We select the non-assigned and assign them to mixer, which contains the boundary condition information for the mixer. Next, since this is a conjugate heat transfer simulation, when we simulate the metal temperature inside the mixer, we need to cap the mixer. So we create 8 new surfaces. We do that by patching. We select a list of edges and use a box select. By going from left to right, we only select those edges which are entirely within the box. So you can see that we can quickly patch these holes with the patch tool. Now that we have finished creating all of the triangles necessary to close off the domain properly, we go to Boundary, Flag, select by Boundary. We select any one of the new triangles since they're all in the non-assigned boundary, and we simply click Apply to assign them to the mixer ends boundary. So this means all of the new triangles for mixer ends and the mixer respectively receive the same boundary conditions that the old geometry received. This ensures complete consistency in boundary conditions from the prior analysis to the new analysis we will run. Now we just show the geometry that will be run in the new Converge simulation. So now our geometry, our case setup is complete for our next simulation with Converge. We simply export the input files and we can run our new Converge simulation, and you're ready to test your new geometry.
Great, Dan. Thank you. So there's a good chance that if, as most design review meetings occur where CFD results are presented, one of the primary things that next steps are to make some change in the geometry. Well, here's where you can make a change in the geometry and have cases running before anybody has a chance to type up the meeting minutes. It's really just that simple, because all you need to do is drop in that new geometry like Dan showed. So let me finish up with a couple additional slides. Just a quick summary here on some of the work that we've done and we've shown you here today. Certainly detailed decomposition gives you that ability to predict urea deposits. We've seen it validated in some of the work that Dan's done. And one of the key things that we've done is that we have accelerated the simulation time. So now you're able to get minutes of simulation time. 5 to 10 minutes is now quite feasible. Of course, you may want to run, you may say, hey, my experiment is on the order of an hour. But our feedback from customers is that 5 to 10 minutes is enough to begin to see appreciable amounts of deposits, and that having that information is certainly key in helping them guide their decisions. So detailed decomposition is also just about as fast as simple urea decomposition. So we encourage you to give that a try. Converge does offer a wide range of urea SCR after-treatment applications, all the way from sort of simple pressure drop and uniformity simulations to incorporating spray wall interactions and films, like I said, identifying deposit risk, and looking at surface chemistry as well. So just like Isuzu Americas has done, we encourage you to take a look at it at Converge. Customers are actively testing. I can't tell you all the customers, but you can imagine some of the major manufacturers in the world are looking at Converge right now. That's something I can say, and validating on their own cases. So if you'd like to learn more, we encourage you to please do register to receive or sign on to our mailing list on convergecfd.com/mailing list there. You've got my contact information there. You can also send in an email to info@convergecfd.com. So we encourage you to look us up and ask further questions. There are a number of technical papers, the work that Dan talked about today, and some additional validation work on the detailed decomposition mechanism are submitted for next year's SAE, but we also have the papers from Isuzu and other validations that we've done that are available to you. We've got tutorials, detailed decomposition tutorials and validation cases you can run yourself, and a wide range of training materials. Please do look for future webinars that we have, not only on after treatment, but also looking at other applications. Before I go to the thank you slide, and while I'm on the thank you slide, we just had a couple extra minutes here before the top of the hour. I've been looking at some of the really good questions that have been asked, and there's a few common questions or on common topics, so I just wanted to sort of take those here. And so one question was, or a number of questions have asked about validations of urea deposit predictions on commercial systems, where we showed mostly work on some fundamental validation cases today. We have been doing that work. We are able to show you that work, of course, that Isuzu Americas published. Unfortunately, we're not able to share the commercial work that we've done with other companies under NDA. So we do encourage you to please, if you know of some publicly available validation cases that look like an actual urea SCR system, let us know. And if you're able to share one of your cases with us under NDA, we'd be happy to look at that as well. Another series of questions were about the reaction rates. Can you see those for the detailed decomposition mechanism inside of CONVERGE? And the answer is yes, you can see them. Because one of the follow-on questions is, if you have some data, if I have data, can I tune that mechanism to those data? And the answer to that is yes, you can, for both the detailed decomposition mechanism and some of the semi-empirical parameters in the urea risk analysis as well. And then, a question that we get asked all the time. We're trying to build towards what the customer's desire is and needs are for modeling urea deposits. And so the common question we get is, hey, once we start growing these deposits, can you actually deform the geometry to represent the geometry change that happens with that deposit as it grows? Maybe it changes its growth rate, or it maybe doesn't grow as much in certain parts as it does when it is just a nice clean pipe. And the answer to that is yes, we are working on that. We don't have anything to show you on that, but I'd be happy to talk to anyone that would like to about sort of what you're looking for. You can think of, once you do get the growth rates that we're seeing from the detailed decomposition analysis, there really is no better code in the world to do that automatic deformation of the geometry because the mesh is created at every time step at runtime. So we think we've been a great advantage when we implement that capability, but that is part of our future work. So with that, I'm going to conclude the webinar, but thank you very much for joining. So we encourage you to continue sending in questions. I know I haven't answered all of them while I've been talking, but I'll do my best to get through everyone. We will reach out to every one of you. So I'd like to thank Dan and Tiffany as well for their participation in this webinar. So thank you very much, and goodbye.